Good morning everyone. Welcome back to online classes of Vlsi design. So it's been a long gap between your previous classes and this present class. I hope you all remember what were the previous class we have all discussed about. Okay, we have seen in last class we have seen about the Cmos inverters and pull up to pull down ratio of one Cmos inverter driven by one more another Cmos inverter. And one was the last topic of that we have discussed in our previous chapter was pull up to pull down ratio for an Cmos inverter driven through one or more pass transistors. Correct? I hope you all remember about the pass transistors. What is meant by pass transistor? It's a if you are connecting all the transistors in series, then they will be acting like a switch. So it is an isolated nature of your gate which allows your transistor which will be acting like a switch. So that is what we call as pass transistors. So we have seen two different pull up to pull down ratios, which is nothing but your enhancement mode and depletion mode transistors, that will be called as your pull up to pull down transistors. So I hope you are clear up to the last topic of your Cmos inverters. Then subtopics of pull up to pull down ratio of one Cmos inverter driven by another Cmos inverter. That is one of the important topic. And another one was pull up to pull down ratio of an Cmos inverter when is driven by one or more pass transistors. Correct? So that was up to last class. So in today's class we are going to discuss about the Cmos inverters. I think everyone knows about the Cmos inverter. It's nothing but the combination of your PMOS inverter as well as your NMOS inverter. This is your PMOS inverter as well as your NMOS inverters, right? So why we require these inverters? Because without inverters, if you are designing any electronic device, or any logical device or any programming, it's very difficult. Without inverter, we can't do any digital design. So inverter is very important part of your all digital designs. We are having three basic gates you are having: AND, OR and inverter. Without inverter we are not able to getting XOR or NOR or NAND. So this is the one of the very important part of your logical design or the digital design circuits. Without inverter we are unable to design any particular circuit. Fine. So the inverter is very important part of all the logical design. Out of that one we are going to see the Cmos inverter today. Okay, so Cmos transistor is designed by using your both combination of BiCMOS transistor as well as your NMOS transistor. So all the logic or the complex structures like NAND gates, adders, multipliers and microprocessor that can be used or utilized very nicely or easily by using your inverters. So it is very important part as to run all these digital design devices. Fine. So let's see how your Cmos inverter will be seen. So this is the circuit diagram of your Cmos inverter. So we will be having a PMOS inverter and NMOS inverter, and they both are connected. Fine. Through the gate itself, through the gate they are both are connected, where you will be giving the input voltage as Vin, and the outputs they are connected at the source and drain of your PMOS inverter and source of your NMOS inverter. Gate, drain, source. This is also gate, drain, source. So the output where you will be getting at the source and drain, at the combination part, at the combining part or the meeting point of that particular source and drain, there you will be getting the output as Vout. And VDD is your the input voltage rail, from where you will be getting VSS is nothing but your ground. So in this inverter circuit, if this is the inverter circuit, I hope you are clear with the inverter circuit, nothing but the combination of your NMOS and PMOS inverter. We'll just quickly see how the working will be here. Okay, what is the inverter circuit working and how we are going to see how the current will be obtained, how the voltages will be getting, if you are increasing or decreasing the threshold voltages, etc. Okay, so first see the basic operation, how you will be getting the inputs and outputs for your NMOS inverter. Okay, so in the inverter circuit, if the input is high, means when you are giving Vin is equals to 1. Okay, first I am giving the input voltage as 1 volts. So Vin high, then the lower the NMOS device which closes to discharge the capacitive load. Similarly, if the input is low, the top PMOS device will be on to charge the capacitive load. Nothing but you will be having a capacitor which will be connected from here to the ground. Okay, that is for sure. You will be having a capacitor. So whenever you are giving V in is equals to 1 volts or the high input voltage, your PMOS inverter or the PMOS transistor, that will be 0 on. So whenever your input is high, lower the NMOS device which will be closest, means P will be on and N will be off. So what happens there, if this is the off stage, so there is no path for charging your capacitor. So similarly, if you are having the input is low, 0 volts, your P device will be on, this will be on, and your N device will be off. So there is a path directly which will be able to charge your capacitor. So there is a path to charge the capacitor. So vice versa, whenever you are giving input 0 and 1, there is a possibility to charge and discharge your capacitor over there. So that this circuit will be acting like a switching circuit. Whenever you are giving 0 as the input, you will be getting 1 as the output. The inverter operation is the one, same. If you are giving 0 as the input, 1 will be the output, and if you are giving 1 as the input, you will be getting 0 as the output. So the whatever you qualitatively, this circuit will be acting as a switching circuit. Since the P channel transistor will be having the exactly opposite characteristics of your NMOS transistor. Okay, so whenever you are giving 1 as the input, what happens? Your PMOS will be off, Vn is equals to 1, this will be off, N will be on. Then you will be having as 0 as the output voltage, because you are discharging, your capacitor will be completely discharged because there is no path over here. Whenever you are giving Vin is equals to 0 volts or the low output voltage, your P device will be on. Then there is a path from your VDD or the voltage rail, and that will makes you charge your capacitor load, and the output voltage you will be getting as 1. So vice versa, 0 if you are giving the input, 1 will be the output. If you are giving 1 as the input, you will be getting 0 as the output. So as to get the CMOS transfer characteristics, we have to go through a different 5 regions. There are 5 different regions to show the CMOS transfer characteristics, which is shown in the below graphs, whatever I have given over here. So this is the circuit diagram of your CMOS inverter, correct? So very first I'm considering this, both are the graphs for that one. Very first region I'm considering as a static region, where your P transistor will be on and N transistor will be off. In the last 5th region, your N transistor or the NMOS transistor will be on and PMOS transistor will be off. This is very important, ma. Okay, see, first I'm seeing the CMOS inverter characteristics, which will be having 5 different regions of operation. Fine, we'll see one by one. So in the first region, when V in is equals to 0, I'm giving as logic 0. When V in is equals to logic 0, we have that the P transistor is fully turned on. Here what happens? Here your P transistors will be fully turned on, while your NMOS transistor will be off, because these both are having the opposite characteristics. When P is on, N will be off. Why we have said that? It will be acting as a switch. Okay, so in region 1, whenever you are giving the logic 0, your P transistor will be on and N transistor will be off. So what happens, man? There is no current to flow through the inverter, and the output is directly connected to the VDD. There is no current flow. What happens here? Your NMOS transistor is off, so it is this switch is closed, correct? So this will be open. So there is direct current flow from VDD, nothing but your 5 volts, correct? So it will be coming, some voltage is coming, either 5 volts or 10 volts, that is completely different thing, but this is on. So there is a direct path from your voltage source or the voltage rail that will be coming from through your PMOS transistor, which is on, and you will be getting output as 1, because this is closed. There is no path to directly go to the VSS, yes or no? So whenever you are giving V in is equals to 0 volts, this P in will be on, N will be off. This is the open switch. You will be directly getting your output voltage, or the flow will be there from the current flow will be there from your inverter, and you will be getting the output as V of 1. So there is no current flow through the inverter, and the output is directly connected to the VDD. Hence the output of the voltage will be logic 1. So what as we have, inverter means when opposite output you have to get. Yes, I have given V in as 0 volts over here. I am getting the output as logic 1. This is for your first region. Okay, now we will see the second region 5. What is the region 5? What I have said, P will be off, N will be on. What it means that you are giving V in as logic 1. You are giving the V in is equals to logic 1, where your NMOS transistor is fully on now and PMOS transistor will be fully off. Correct? See, in case you remember also, if there is any capacitor, what happens in the first one, it will be charging. Okay, in the first part whenever you are giving logic 0, after that it will be discharging in your logic region 5 whenever you are giving the logic 1 as the input. So come back to the region 5. V in is equals to logic 1, means you are giving 1 as the input over here, means your NMOS transistor will be on, PMOS transistor will be off. So there is no current flows and the logic 0 will be appearing as the output. There is no path over here. There is no path between your VDD to output voltage. So what you are having, already it is discharged, it is connected to the VDD ground. So what happens, what is the output, you will be getting 0. There is no current, no path from here, from your current source or the current rail. So this is closed, this is open, what it is connected to the ground. So you will be getting output as 0. So logic 1 you have given the input, in VN 1 is, if you are giving 1 input, you are getting the output as 0. Now comes to the region 2. The input voltage has increased to a level which is just exceeding your threshold voltage. I am not saying it is 1.5 or 0.5 or not giving any particular range. We have set some voltage, compulsory some voltage has to be set threshold voltage. I am not exceeding that particular. In region 2, the input voltage has increased to a level which is just exceeding your threshold voltage of your NMOS transistor. So in this NMOS transmitter you are just exceeding in region 2. So what happens? The N transistor conducts and a large voltage will be there between your source and drain. So this region is said to be in your saturation region here, because both you are giving some voltage exceeding your threshold voltage of NMOS transistor. Either not I am giving 0, neither 1. So these both transistors will be on in these regions. In which regions? 2, 3 and 4. In these particular regions they both will be on. So what happens over here? So we are increasing some voltage level and giving the V in is equals to some voltage level which is just exceeding the threshold voltage, which means there is some voltage which is occurring between source and drain. Which is the source and drain? This part. See, this is gate, drain and source. This is source of NMOS transistor and this is drain of your PMOS transistor. So there is a large voltage which is output at your between your source and drain. So the PMOS transistor is also conducting, as I have said, they both are on. It is also conducting, but with only small voltage across it. So this operates in unsaturated resistive region. What I have said, we are exceeding, here we are giving in region 2, we are giving a voltage which is just exceeding the threshold voltage of NMOS transistor. So PMOS transistor will be conducting. It is also conducting, but with a small voltage. If I am going for the region 4, what happens over there? It is all NMOS. Here we will be giving a voltage which just exceeds the threshold voltage of your P transistor, and their N transistor will also be conducting with a only small voltage. Okay, very small voltage. Which that then in that type in region 4, your PMOS transistor will be in unsaturated resistive region. So these 2 and 4 will be similar regions. Okay, so there is a small current flow between the inverters from VDD to VSS. So there will be small current flow, continuously small current flow from VDD to VSS. In region 1 we are having the current flow direct from VDD, we will be getting the output. In region 5 what you are having, there is no current flow, we are getting 0 as the output. Correct? we are giving in 1 input and 0 as the output over here. In the region 2 and 4, what happens? In the first region 2, we are giving a threshold voltage, we are giving a voltage which exceeds the threshold voltage of NMOS transistor. Please make a note whatever I am saying, okay? Then in region 4, we are giving a voltage which exceeds the threshold voltage of P transistors. In both the regions, both the transistors will be conducting, but with very small voltages, and one of the transistors will be in unsaturated resistive region. So there is a small current flow will be going, through your VDD to VSS path, correct? So if you wish to analyze the characteristics or the whole behavior of the CMOS characteristics, what you have to do, we have to equate the P device resistive region with the N device saturation region, and we can obtain the relationships. If you want to do any mathematical expressions, then we have to equate these two regions. Which to P device resistive region, we have to equate it to N device saturation current region. Then you will be getting the VI characteristics of your CMOS inverter. That is not that much important, okay? Now see, region 4, as I have already said, it is similar to the region 2, but with the roles of P and N transistors will be reversed. What we will be doing there, here in that particular region, we are giving a voltage which exceeding the threshold voltage of P region, where your P will be, where N will be conducting with a small current. So they both are similar, 2 and 4 regions will be similar. However, the current magnitudes in the region 2 and region 4 are small, and most of the energy will be consumed in switching from one stage to another state. So this is one thing, a drawback over there. So what in region 2, what in region 3, the current magnitudes are very small. I have said that if one of the region, if you are working, another transistor will be of very small voltage, it will be conducting with only small voltage across it. So most large of energy will be consumed for switching from one state to another state. So in region 3, in which the inverter exhibits gain, and in which both the transistors will be in the saturation region. In region 2 and region 3, one will be in saturation region, another will be in unsaturation region, and the energy will also be consumed. So in region 3, what we are having, they both will be exhibiting gain, means we will be getting high gain in region 3, and both the transistors will be in saturation region. So the current in each device must be same. In third region, the current will be same in the each devices, since their transistors are connected in series, and these transistors will be connected as voltage sources. I have given in pull up to pull down transistors derivation what we have seen, where we have seen how we are using the transistors as current sources. I'll give the link of that particular video also, just go through that one once. Okay, so since we can write, as we are having the same current in both the devices, we can write the IDSP, nothing but drain to source current of your P transistor is equals to minus IDS, drain to source current of your N transistors. This equation we have got is a saturation and saturation region, where VDD is equals to 0 here in N transistor. So these equations we have got from the last videos where we have derived. Okay, since both the transistors are in saturation region, they act as the current sources. So the equivalent circuit in this region is two current sources in series between VDD and VSS, with the output voltage which is coming from their common point. I don't have any pen, I don't have shown you. These two regions means these both transistors, they can be made it as current sources, means two circles will be there. Go back to your NMOS inverter video, there I have shown the picture that how we are converting, showing your transistors as current sources. So these two currents, these two transistors may be connected as current sources both in the series, and the output will be between the rail VDD to VSS, and that will be coming from their common point. Common point means this one. This is your common point. These two will be acting as the current sources, and the path will be from VDD to VSS. So this is how your CMOS transistor will be working and the operation. Okay, I hope you are all clear with the CMOS inverter and their operations. What are the 5 different regions how you are going to operate this CMOS inverter? Clear, ma? Now next topic is your BiCMOS inverters. Okay, now what is meant by CMOS? You are using 2 CMOSs. Yes, so so for any NMOS and CMOS logic circuitry, a basic logic element is your CMOS inverter circuit. Inverter is nothing but which gives your one of the important part of your digital design or the important logic design. So whenever for any NMOS or PMOS or CMOS logic circuitry, the basic logic element is your inverter circuit. So when designing a BiCMOS, the logic approach is to use the MOS switches. Okay, we have to get the MOS switches as to perform the logical operations. All these MOS switches will be performing a logical operation, and these bipolar transistors are used to drive the output loads. So why we are going for the BiCMOS inverter is that, so for as to have the logical operations, we are using this PMOS and NMOS circuitry, but as to drive your output voltages, what we are using this bipolar transistor. So in combination of your switches and bipolar transistors is nothing but your BiCMOS transistor or a BiCMOS inverter, where you will be having combination of MOS switches and transistors, bipolar transistor. Combination of MOS switches and bipolar transistor is called as BiCMOS inverter. Here your MOS switches are used for getting your logical functions, and bipolar transistors are used to drive the output voltages. Okay, the simpler bipolar inverter is given in this way. Here you are having 2 transistors and 2 MOS switches. Okay, where T1 and T2 are 2 bipolar transistors. These both are transistors, whereas your T3 is your NMOS transistor and T4 is your PMOS transistor. Clear? T1, T2 are bipolar transistors, T3 is your NMOS transistor and T4 is your PMOS transistor. Okay? Clear? Let's see the working operation of this one, and keep in mind that these both are in enhancement modes. Okay, they both are being in your enhancement mode devices. Okay, here also we are having different as it is also inverter. We have seen NMOS inverter. Inverter is nothing but getting 0. If you are giving the 0 as the input, you get the output as 1. So we have seen NMOS inverter, then CMOS inverter, then lastly is your BiCMOS inverters. So when it comes to your BiCMOS inverters, when Vin is equals to 0 volts, that is nothing but ground, T4 is on. Listen carefully, see the diagram. So when Vin is equals to 0 volts, I am giving Vin input as a 0 volts, then T4 will be on. What is the T4? Which is the T4? It is nothing but your PMOS transistor. PMOS transistor will be off, so that T2 will be in non-conducting stage. See, this T4 is directly connected to your T2 transistor, one of the bipolar transistors, right? So I am giving Vin is equals to 0 volts. So what happens over here? T4 will be off. Okay, and T4 is directly connected to the V rail, correct, input voltage rail. So if it is off, so there is no current flowing through this T2 also. So your T2 will be in non-conducting state. These two are non-conducting state. But T3 is on. What is T3? NMOS transistor is on and supplies the current to the base of your T1. This is base, correct? T1's base, you are getting the voltage from T3 because it is directly connected to the voltage rail of this one. So but T3 is on and supplies the current to the base of T1, which will conduct and act as the current source to charge the load CL towards the 5 volts VDD. Correct or not? So these two path is off now. There is no current flowing from T3 and T4 and T2. Correct? So PMOS is completely off. Now NMOS is on. So it will be driving the current from T3 to T1 through the base of T1, and from this one your capacitor CL will be loaded towards the 5 volts. Correct? Now second one. the output of the inverter voltage will raise to 5 volts. Means what happens here, we will be getting 1 as the output. We are given the 0 as the input, it is charged to 5 volts, and you are getting the volts, you are getting the output as 1 volt, correct? But this voltage is less than the emitter voltage VBE of T1. This is the one point, that the voltage what you have obtained over here, that voltage is comparatively less than the VBE or the emitter voltage of your transistor, bipolar transistor T1. That was the first part. Now we are giving Vn is equals to 5 volts. First we have given 0 volts. Now we are giving 5 volts. When we have given 0 volts, you get the you have got the output as 5 volts. Correct one? Now we are giving the Vin is equals to 5 volts. Now what happens if it is given 5 volts over here? Means it is logic 1. Assume that. So your T3 will be off now. Yes or no? T3 means your NMOS transistor. This NMOS transistor is off now. Now PMOS transistor is on. If PMOS transistor is on, then you are getting the voltage or the current flow from this current rail, and which will be conducting now? T2 will be in conducting region. So T4 will be on and will supply current to the base of T2. So it will be bringing the current from here and it will be supplying current to the T2. But here the output of the inverter now falls from 5 volts to 0 volts because the capacitor will discharge now. We already had charged the capacitor through T3 when we had got Vin is equals to 0 volts. Now we have Vin is equals to 5 volts, but it is already charged in the first region only. Now it will be in discharging region. So how much it will be discharging? It will be falling from 5 volts to 0 volts. So what is the output you will be getting over here? That is 0 volts. You have got Vin is equals to 5 volts as the input. You got the 0 volts as the output. So that is how your CMOS inverter will be working. See, so T1 and T2 will present low impedances when turned on in saturation region, and load CL will be charged or discharged rapidly. So what is that one, ma? So we T1 and T2 will both will be in low impedances over here, and the presence of DC path from VDD to ground through T4 and T2 is not a good arrangement. This is a very important note. This is the first drawback because it's not having the proper arrangement, because as to implement, since there will be significant static flow where Vin is equals to 1. I'll repeat it once again. The presence of DC path, your direct current path from your T4 to T2 is not a good arrangement. You are directly getting the voltage from here, because as to implement there will be a significant static flow when Vin is equals to 1. When we are giving 1 as the input voltage, there is continuous running of the voltage which makes your circuit slow. So as to avoid that one, what we are going, but it has a problem that there is no discharge path for the current from base to either bipolar transistor when it is being turned off, which will slow down the action of the circuit. So as to improve that one, we are removing the direct path from your T4 to the VDD rail and connecting it to here. So the improved version of that is the DC path through T4 to T2 will be eliminated, but the output voltage swing is now reduced. So there is first drawback was that we are having a direct path. Okay, we are having a direct path, but due to having this direct path, there is no discharge path of your current. You are directly getting it from here, you are charging, and there is no discharge path, particular path. So that's the reason what we are doing. We are removing the direct path from your T4 to rail and connecting it over here at a T1 path at the common point. Okay. So due to this one, these drawback, what is a drawback which will be slow down the action of the circuit? This will be stopped. You are now slow. What is the drawback? First drawback, by having the direct path from T4 to T2 was here slowing down the circuit. So we have eliminated the direct path. We have that drawback has been removed. Now your circuit is improved. But here but one more drawback we have obtained over there. The output voltage swing is now reduced. You have to get the proper output voltage swings. If you are not getting the proper output voltage swings, then it will be a drawback for your circuit. So as to improve that one, what you are using, we are using a resistors in between these transistors. Okay, as to get the proper swings in this one, in this particular BiCMOS circuit, we are using the transistor. So an improved inverter arrangement is using the resistor, which is considered, which provides the improved swing of your output voltage. We have to get the proper output voltage swings, and that is obtained by using the resistors in your bipolar circuit, bipolar inverter circuit. Okay, when each bipolar transistor is turned off, and also provides a discharge path from the base current. It also provides proper discharge path from your base current. From here, see, here you are having the base of your T1, it is having the proper discharge path also. So it is the good arrangement of your BiCMOS inverter. But since in the first class itself I have told that, I think everyone remember, that resistors will be consuming lots of space on your chip. We are using the resistors here, correct? In the first or second class I have told resistors will be consuming the lots of space on the chip. See here. So but these resistors are not always suitable, because they will be having some they will be taking the space, or they will have they are consuming space on your chip. So the other arrangements are used by using the transistor. So what we are doing, we are replacing the resistors by transistors. So T5, this is a T5 and this is T6 are the two transistors which are replaced by your which one? Resistors. So these transistors T5 and T6 are turned on when T1 and T2 are turned off. See the same arrangement here in between T1 and actually what I have drawn here is T3, T4. These are opposite in the first one. Just make some arrangements and go through this video. Okay. So this T1, and between T1 and T4 you will be having this T6, and T2 and T4 you will be having some, actually it is T3 over here. Here you make just change the numberings. So same arrangement, between these two I am having one resistor, so between these two I am having one transistor, and between these two transistors I am having one more transistor. So when these both are turned on, when T1 and T2 will be turned off. So this is how your improved version of your BiCMOS inverter will be working. I hope you are all clear with these two topics, CMOS inverters and BiCMOS inverters. CMOS inverters, where you will be having the combination of PMOS and NMOS transistors, and there are 5 working regions over there. Okay, in BiCMOS inverters you are using 4 transistors. Okay, 2 are what is the combination of BiCMOS inverters? We are having MOS switches along with your bipolar transistors, right? So we have got the proper arranged with removing all the drawbacks in this one. So I hope you are clear with this today's class. In case of any doubts, please let me know. Okay, thank you.